HTTP methods. HTTP provides a standard set of methods that form the interface for a resource. Since the original HTTP spec was published, the patch method has also been approved. As shown earlier in Figure 1 to 4, the method appears as part of the request itself. N. ext is a description of the common methods API authors implement. GET retrieves information from a resource. F. The resource is returned. The server should return a status code 200 OK. Head identical to a GET, except it returns headers and not the body. Post requests that the server accept the enclosed entity to be processed by the target resource. As part of the processing, the server may create a new resource, though it is not obliged to. If it does create a resource, it should return a 201 created or 202 accepted code and return a location header telling the client where it can find the new resource. If it does not create a resource, it should return a 200 OK or a 204 no content code. In practice, Post can handle just about any kind of processing and is not constrained. Put requests that the server replace the state of the target resource at the specified URI with the enclosed entity. If a resource exists for the current representation, it should return a 200 OK or a 204 no content code. However, if the resource does not exist, the server can create it. If it does, it should return a 201 created code. The main difference between Post and Put is that Post expects the data that is sent to be processed, while Put expects the data to be replaced or stored. Delete requests that the server remove the entity located at the specified URI. If the source is immediately removed, the server should return a 200 code. If it is pending, it should return a 202 accepted or a 204 no content. Options requests that the server return information about its capabilities. Most commonly, it returns an allow header specifying which HTTP methods are supported, though the spec leaves it completely open-ended. For example, it is entirely feasible to list which media types the server supports. Options can also return a body, supplying further information that cannot be represented in the headers. Patch requests that the server do a partial update of the entity at the specified URI. The content of the patch should have enough information that the server can use to apply the update. If the resource exists, the server can be updated and should return a 200 OK or a 204 no content code. As with Put, if the resource does not exist, the server can create it. If it does, it should return a code of 201 created. A resource that supports patch can advertise it in the allow header of an options response. The accept patch header also allows the server to indicate an acceptable list of media types the client can use for sending a patch. The spec implies that the media type should carry the semantics to communicate to the server the partial update information. JSON patch is a proposed media type in draft that provides a structure for expressing operations within a patch. Trace requests that the server return the request it received. The server will return the entire request message in the body with a content type of message/HTTP. This is useful for diagnostics, as clients can see which proxies the request passed through and how the request may have been modified by intermediaries. Conditional requests. One of the additional features of HTTP is that it allows clients to make conditional requests. This type of request requires the client to send special headers that provide the server with information it needs to process the request. The headers include if match, if non-match, and if modified since. Each of these headers will be described in further detail in Table B2 in Appendix B. A conditional GET is when a client sends headers that the server can use to determine if the client's cached representation is still valid. If it is, the server returns a 304 not modified code rather than the representation. A conditional get reduces the net work traffic as the response is much smaller, and also reduces the server workload. A conditional put is when a client sends headers that the server can use to determine if the client's cached representation is still valid. If it is, the server returns a 409. Preconditions failed. A conditional put is used for concurrency. It allows a client to determine at the time of doing the put whether another user changed the data. Method properties. HTTP methods can have the following additional properties. A safe method is a method that does not cause any side effects from the user when the request is made. This does not mean that there are no side effects at all, but it means that the user can safely make requests using the method without worrying about changing the state of the system. An idempotent method is a method in which making one request to the resource has the same effect as requesting it multiple times. All safe methods are by definition idempotent. However, there are methods that are not safe and are still idempotent. As with a safe method, there is no guarantee that a request with an idempotent method won't result in any side effects on the server, but the user does not have to be concerned. A cacheable method is a method that can possibly receive a cached response for a previous request from an intermediary cache. Table 1-to-1 lists the HTTP methods and whether they are safe or idempotent. Table 1-to-1. HTTP methods. Method safe idempotent cacheable get size head size post no putin wa yes no delete no yes no option size no. Method safe idempotent cacheable patch no yes no trace yes no. Of the methods listed, the most common set used by API builders today are get, put, post, delete, and head. Patch, though new, is also becoming very common. There are several benefits to having a standard set of HTTP methods. Any HTTP client can interact with an HTTP resource that is following the rules. Methods like options provide discoverability for the client so it can learn how those interactions will take place. Servers can optimize. Proxy servers and web servers can provide optimizations based on the chosen method. For example, cache proxies know that GET requests can be cached. Thus, if you do a GET, the proxy may be able to return a cached representation rather than having the request travel all the way to the server. Headers. HTTP messages contain header fields that provide information to clients and servers, which they should use to process the request. There are 4 types of headers: message, request, response, and representation. Message headers apply to both request and response messages and relate to the message itself rather than the entity body. They include headers related to intermediaries, including cache control, pragma, and via. Headers related to the message, including transfer encoding, and trailer. Headers related to the request, including connection, upgrade, and date. Request headers apply generally to the request message and not to the entity body, with the exception of the range header. They include headers about the request, including host, expect, and range. Headers for authentication credentials, including user agent and from. Headers for content negotiation, including accept language, and accept encoding. Headers for conditional requests, including if match, if none match, and if modified since. Response headers apply to the response message and not the entity body. They include headers for providing information about the target resource, including LLO and server. Headers providing additional control data, such as age and location. Headers related to the selected representation, including ETAG, last modified, and vary. Headers related to authentication challenges, including proxy authenticate and www authenticate. Representation headers apply generally to the request or response entity body content. They include headers about the entity body itself, including content type, content length, content location, and content encoding. Headers related to caching of the entity body, including expires. For a comprehensive list and description of the standard headers in the HTTP specify cation, see Appendix B. The HTTP specification continues to be extended. New headers can be proposed and approved by organizations like the IETF Internet Engineering Task Force or the W3C. World Wide Web Consortium as extensions of the HTTP protocol. Two such exam pleas, which are covered in later chapters of the book, are RFC 5861, which introduces new caching headers, and the course specification, which introduces new headers for cross-origin access. HTTP status codes. HTTP responses always return status codes and a description of whether the request succeeded. It is the responsibility of an origin server to always return both pieces of information. Both inform the client whether or not the request was accepted or failed and suggest possible next actions. The description is human-readable text describing the status code. Status codes range from 4xx to 5xx. Table 1 to 2 indicates the different categories of status codes and the associated references in FBIs. Table 1 to 2. HTTP status codes range description reference 1xx. Request has been received and processing is continuing. http://tools.ietf.org/html/draft/ietf FBIs P2 Semantics 21 Section 7.22xx. Request has been accepted, received, and understood. http://tools.ietf.org/html/draft/ietf FBIs P2 Semantics 21 Section 7.3. Range description reference 3xx. Further action is required to complete the request. http://tools.ietf.org/html/draft/ietf FBIs P2 Semantics 21 Section 7.44xx. The request is invalid and cannot be completed. http://tools.ietf.org/html/draft/ietf FBIs P2 Semantics 21 Section 7.55xx. The server has failed trying to complete the request. http://tools.ietf.org/html/draft/ietf FBIs P2 Semantics 21 Section 7.6. Status codes can be directly associated with other headers. In the following snippet, the server has returned a 201, indicating that a new resource was created. The location header indicates to the client the URI of the created resources. Thus, HTTP clients should automatically check for the location in the case of a 201. http://1.1201 created cache control no cache pragma no cache content type application/JSON. Charset equals UTF-8 location http://localhost 8081/API/contacts/6 content negotiation. HTTP servers often have multiple ways to represent the same resources. The representations can be based on a variety of factors, including different capabilities of the client or optimizations based on the payload. For example, you saw how the contact resource returns a vCard representation tailored to clients such as mail programs. HTTP allows the client to participate in the selection of the media type by informing the server of its preferences. This dance of selection between client and server is what is known as content negotiation, or CNEG. Caching. As we learned in method properties on page 14, some responses are cacheable. Line particular, the responses for GET and HEAD requests. The main benefit of caching is to improve general performance and scale on the Internet. Caching helps clients and origin servers in the following ways. Clients are helped because the number of round trips to the server is reduced, and because the response payload is reduced for many of those round trips. Servers are helped because intermediaries can return cached representations, thus reducing the load on the origin server. An HTTP cache is a storage mechanism that manages adding, retrieving, and removing responses from the origin server to the cache. Caches will try to handle only requests that use a cacheable method. All other requests with non-cacheable methods will be automatically forwarded to the origin server. The cache will also forward to the origin server requests that are cacheable, but that are either not present in the cache or expired. BBS defines a pretty sophisticated mechanism for caching. Though there are many finer details, HTTP caching is fundamentally based on two concepts: expiration and validation. Expiration: a response has expired or become stale if its age in the cache is greater than the max minimum age, which is specified by the max age cache control directive in the response. It will also expire if the current date on the cache server exceeds the expiration date, which is specified by the response expires header. If the response has not expired, it is eligible for the cache to serve it. However, there are other pieces of control data. See caching and negotiated responses on page 19 coming from the request and the cached response that may prevent it from being served. Validation: when a response has expired, the cache must revalidate it. Validation means the cache will send a conditional GET request. See conditional requests on page 13 to the server asking if the cached response is still valid. The conditional request will contain a cache validator, for example, an if modified since header with the last modified value of the response and / or an if none match header with the response's etag value. If the origin server determines it is still valid, it will return a bodiless response with a status code of 304 not modified, along with an updated expiration date. If the response has changed, the origin server will return a new response, which will ultimately get served by the cache and replace the current cached representation. Serving stale responses: HTTP does provide for caches to serve stale responses under certain conditions, such as if the origin server is unreachable. In these conditions, a cache may still serve stale responses as long as a warning header is included in the response to inform the client. HTTP Cache Control Extensions for Stale Content, by Mark Nottingham, proposes new cache control directives. See cache behaviors on page 20 to address these conditions. The stale while revalidate directive allows a cache to serve up stale content while it is in the process of validating it in order to hide the latency of the validation. The stale if error directive allows the cache to serve up content whenever there is an error that could be due to the network or the origin server being unavailable. Both directives inform caches that it is okay to serve stale content if these headers are present, while the aforementioned warning header informs clients that the content they have is actually stale. Note that RFC 5861 is marked as informational, meaning it has not been standardized. Thus, all caches may not support these additional directives. In validation: once a response has been cached, it can also be invalidated. Generally, this will happen because the cache observes a request with an unsafe method to a resource that it has previously cached. Because a request was made that modifies the state of the resource, the cache knows that its representation is invalid. Additionally, the cache should invalidate the location and content location responses for the same unsafe request if the response was not an error. Etags: an entity tag, or etag, is a validator for the currently selected representation at a point in time. It is represented as a quoted opaque identifier and should not be parsed by clients. The server can return an etag which it also caches in the response via the etag header. A client can save the E-tag to use as a validator for a future conditional request, passing the E-tag as the value for an if match or if none match header. Note that the client in this case may be an intermediary cache. The server matches up the E-tag in the request against the existing E-tag it has for the requested resource. If the resource has been modified in the time since the E-tag was generated, then the resource's E-tag on the server will have changed and there will not be a match. There are two types of E-tags. A strong E-tag is guaranteed to change whenever the server representation changes. A strong E-tag must be unique across all other representations of the same resource. E.g., 1, 2, 3, 4, 5, 6, 7, 8, 9. A weak E-tag is not guaranteed to be up to date with the resource state. It also does not have the constraints of being unique across other representations of the same resource. A weak E-tag must be preceded with W/EG, W/1, 2, 3, 4, 5, 6, 7, 8, 9. Strong E-tags are the default and should be preferred for conditional requests. Caching and negotiated responses. Caches support the ability to serve negotiated responses through the usage of the vary header. The vary header allows the origin server to specify one or more header fields that it used as part of performing content negotiation. Whenever a request comes in that matches a representation in the cache that has a vary header, the values for those fields must match in the request in order for that representation to be eligible to be served. The following is an example of a response using the vary header to specify that the accept header was used. http://1.1200 OK content type application/JSON. Charset equals UTF-8 content length 183 vary. Accept cache behaviors. The cache control header gives instructions to caching mechanisms through which that request/response passes related to its cacheability. The instructions can be provided by either the origin server as part of the response, or the client as part of the request. The header value is a list of caching directives that specifies things like whether or not the content is cacheable, where it may be stored, what its expiration policy is, and when it should be revalidated or reloaded from the origin server. For example, the nocache directive tells caches they must always revalidate the cached response before serving it. The pragma header can specify a nocache value that is equivalent to the nocache cache control directive. Following is an example of a response using the cache control header. In this case, it is specifying the max age for caches as 3600 seconds 1 hour from the last modified date. It also specifies that cache servers must revalidate with the origin server once the cached representation has expired before returning it again. http://1.1200 OK cache control must revalidate, max age equals 3600 content type application/JSON. Charset equals UTF-8 last modified WED, December 26, 2012 220,515 GMT date Thursday, December 27, 2012 010515 GMT content length 183. For a detailed walkthrough of caching in action, see Appendix D. For more on HTTP caching in general, see Things Caches Do, by Ryan Tomeko, and How Web Caches Work, by Mark Nottingham. Authentication. HTTP provides an extensible framework